So everything we've been talking about up to this point is thinking about the electron configurations of neutral atoms. Atoms as they appear on the periodic table, where we have the same number of electrons and protons in the atom. But ions, as we've seen, are really an important part of chemistry as well. We've seen lots of different ionic compounds and things that dissolve in solution to form ions. And so understanding the electron configurations of ions is really important as well. And this helps to explain some of the things you've already learned about ions. So we'll start first thinking, and here we're just thinking about monatomic ions, so not considering polyatomic ions in this chapter. Everything here is about single atoms or ions that are made out of single atoms. So we'll start with the S block and the P block. These are sort of the easiest ions to make sense of. And so let's go ahead and jump over to our periodic table. So S block, again, that means our alkali metals and our alkali earth metals. And our P block meaning our elements over here. And primarily we're going to look up in this corner of the periodic table, not so much at our metalloids and metals that are down over here. So let's look at the S block. So let's think about the electron configurations here of the neutral atoms. So again, our S block, these are our alkali metals and alkali earth metals. They're all going to have a configuration that looks like noble gas core electrons, and then have NS, whatever the last value of N is, depending on the row of the periodic table, either 1 or NS2. This would be the alkali metals, the first column, and the NS2 would be the alkali earth metals. Now, having a configuration the same as a noble gas tends to be a low energy configuration for atoms. And so when ions form, they want to form electron configurations that are the same as that noble gas configuration. For these S block, right, we're talking about the S block. For these metals, things like sodium, for example, we know that sodium wants to form a singly charged ion, Na+, a positively charged singly charged ion. What that means is that it loses an electron. And now we can understand why that is. If we look at sodium, sodium is in the third row of the periodic table, so its configuration is the core will be neon and then one electron and 3s orbital. Right, so we'll have neon for the core electrons and then 3s1. Now the easiest way for sodium to be like neon, to have the same electron configuration, is to lose this 3s electron. So once it loses that 3s electron, its configuration becomes just the same as that core set of neon electrons. So that is the easiest way for the S block elements. And that's why they all form positive ions. They all lose electrons because they either have 1 or 2 electrons to lose. And that's why all of our alkali metals form +1 ions and our alkali earth metals form +2 ions. And after they become ions, their electron configuration will just be whatever noble gas core that's left after we lose those S electrons. So just those core electrons will be left behind, and we have a sodium plus or a +1 or +2 ion, and they're happy for that. So this follows the same rules that we learned earlier in the year, but this is just an explanation now as to why it does this. The S block elements want to lose those electrons. The P block elements, on the other hand, let's look at something like sulfur or fluorine. We'll start with the halogens here. Let's think about the electron configuration of something like chlorine. So again, we have that same neon core for chlorine. Let me give myself some space. So thinking about chlorine, we know that chlorine forms a -1 ion. It gains an electron. Now let's think about it in terms of the electron configuration. So it has that same neon core that sodium did that we just talked about. And we'll have 2 electrons in 3s orbitals, and then we'll fill in the 3p orbitals. And chlorine had 5, if we come back here and count, 1, 2, 3, 4, 5 electrons that went into that 3p that go into that 3p orbital. Now, To lose all 7 of those electrons would be very difficult. And so chlorine doesn't form a, chlorine 7 plus ion, losing 7 electrons. Instead, it's much easier to just add 1 more electron into the p orbital so that we get the configuration of neon, 3s2, 3p6, and this becomes the same electron configuration as the noble gas right next to chlorine, which is argon. And so it has achieved that electron configuration that is very similar to a noble gas, or is the same as a noble gas by gaining an extra electron. And so that's why chlorine, when it ionizes, forms a -1 ion. The same will apply to every single one of the halogens, all of these elements here in this second to last column of the periodic table. These all have a P5, NP5, so depending on which row you're looking at. So fluorine is 2p5, chlorine is 3p5, bromine is 4p5, etc., etc. And to finish filling that orbital, it's easiest to gain 1 electron. And so that's why all these form -1 ions when they form ions. We can go to the next column over, and we've learned this as well. Oxygen's lacking 2 electrons, so it has a P4 configuration. So it needs 2 extra electrons and forms O2 minus. It forms a -2 charge ion. Same for oxygen and sulfur and selenium. And we can go even one more. Nitride forms -3. We have to add 3 extra electrons to get it all the way to the next noble gas configuration. Okay, so for the S and P block elements, the S block, we're going to lose electrons to form positive ions. They're metals, they behave that way. And the P block elements, we need to gain electrons to finish filling that orbital. So that's the straightforward way to look at forming ions. And this follows all the same rules. This is just an explanation as to why those rules exist in the first place. It's all about these atoms achieving that noble gas electron configuration, either by losing electrons from s orbitals or adding electrons into p orbitals to finish filling them.